problem. It goes to infinity. It goes to infinity. So the only way you can actually solve it is if it's geometric, which it turns out it is. It's geometric because it's an exponential function. You can find some infinite sums of geometric sequences. The only way you can find it is if your r value, the absolute value of r, is less than 1. So it's geometric, it's infinite, so you're going to check your r value. Your r value is right there. It is always the base of your exponent. So if that value, the absolute value of that value is less than 1, you can find the sum. If your r value is less than 1, the absolute value, you can find the sum. So it's infinite, it's geometric, we can find the sum because our r value is less than 1 or the absolute value. The sum formula is your first term divided by 1 minus r. The second twist in this problem is a sub 1 is actually not your first term in this one. Yes, it's going to be negative 1. We're going to plug in a negative 1 to get our first term. So really, instead of a sub 1, we're looking at a sub negative 1 in this case, because they tell you have to start at negative 1. So to find that value, you're going to plug negative 1 in. So we're going to have 3 times 1 over 2 to the negative 1 minus 1, which equals 3 times 1 half to the negative 2. Another twist. We have a negative exponent. Maybe we haven't used those in a while. A negative exponent only tells you to take the reciprocal. A negative exponent just means reciprocal. So what this is more basically saying is doing 2 over 1 squared. Negative just means take the reciprocal. 2 squared is 4 times 3 is 12. So our first term is 12. So our sum is going to equal our first term, which is 12, over 1 minus r, which is 1 half. Well, that's 12 over 1 minus 1 half. 1 minus 1 half is 1 half. 12 divided by 1 half is really keep, change, flip. 12 times 2 over 1, or 24, or 24.
Yeah.
I don't know how to respond to their reaction. Yeah, everyone should clap every time I solve something. No, don't. No, please, don't. No, please, no. And on that, what questions do we have from the homework?
No question.
No, I saw your hand go up really quickly. 47. No. Well, then I won't answer it. We'll wait till. All right, 47 says phone numbers. How many different 7-digit phone numbers are available in Jamestown if the first 3 digits are 345, 286, or 329? So that means the last 4 digits can be whatever. It could be 000, 001, 002. I'm going to stop there. But our last 4 digits are a pool of, I can be 0 through 9. I can be 0 through 9, 0 through 9, 0 through 9. Well, that's picking one number from each group, right? So that falls into that category. We can just multiply them over and over. We still have to worry about the first 3, correct? Mm-hmm. Well, how many options are there to pick from for the first 3? What was that? Not 1, but
3.
There's 3 different options. So for all of the first 3, we only have 3 options we can pick one from. So we're going to pick one of those 3, one of these numbers, one of these numbers, one of these numbers, one of these numbers. So we're going to multiply all of those together. Does that make sense why it's 3 out front?
Yeah.
We're not going to treat them as 3 individual numbers. It's just 3 choices from there. What was that?
Is that it?
That's it. That is the whole problem there. Yeah.
How do you know when we should use factorials versus just multiplying? That seems to be like a big problem.
You're going to use factorials when it's a permutation problem.
Oh,
Permutation problem is kind of like the joke one where you know you're going to decrease every single time, or you have 100 things, I need to pick 5 of them. You're going to know it's just multiplying straight across if you have just a bunch of groups that you just keep pulling one item from each of those individual groups. Mary?
Sorry, and then so like with exponents also, is that just kind of like if it's the same number multiply?
Yeah, so this would be 3 times 10 to the 4th would be an easier way to write that. All right, Mark, do you have a?
Yeah, 41.
41 says multiple choice test. How many different ways are there to mark the answers to a 6-question multiple choice test in which each question has 4 possible answers? So there's 6 questions. First question. How many possible answers does the first question have? 4. What about the second one?
4.
Next 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 one?
Just
Oh, I thought I was going to get you. All right, so that's 6 questions. We're pulling 1 from each. So that's that fundamental counting theorem. You just need to multiply 4 times 4 times 4 times 4 times 4 since you're just pulling 1 from each one. And your total is going to be 4 to the 6th, or 4,096. Dasha.
Number 7.
Number 7. Is that the ghost one?
Yeah.
Oh. We have ghosts. We have ghosts visiting you. They're visiting you at 1 o'clock, 2 o'clock, and 3 o'clock in the morning. There are 3 ghosts. There's a past, there's a future, and a present, but they don't know when they're going to show up. So they're going to show up in a random order. How many different possible orders are there? So it does ask for a tree diagram. But more specifically, I mean, it's just 3 times 2 times 1. But we'll talk about why that is in just a second. Let's first look at my tree diagram. Kind of like choosing your outfit for the day. In the very beginning, either the past, the future, or the present can show up. At 1 o'clock, one of those 3 can show up. Let's say the past shows up. That means only the future ghost or the present ghost can show up at 2 o'clock. There's only 2 left. Well, let's pretend the future showed up. Only the present's left. That's the last ghost that could possibly show up. So that's 1 branch. Well, if the present showed up, then the future would show up at 3 o'clock. That's another branch. So we'd have a total of 1, 2, 3, 4, 5, 6 possibilities. Another way to think about this. No, that's fine. Another way to think about this is how many ghosts can show up how many possible ghosts could show up at 1 o'clock? 3. Well, yeah, one. But out of... If I just open my eyes, there's 3 possible that could be in front of me. 1 is actually showing up, but it's 3 possible. How many are possible to show up at that next hour?
2.
2. How many at the last one?
1.
1. So it's 3 times 2 times 1.
What?
Whoa. All right, other questions? Ross. 51, what are you asking? Okay, we're taking a test. How many ways are there to choose the answers to a test that consists of 5 true or false, followed by 6 multiple choice tests? So this is really just an offshoot of the one that Mark asked. So the first question is true or false. How many possible ways are there to answer a true or false? 2. So it'd be 2. And then we'd have 2. And then we would have 2. And how many are there? There are 5. 2. So there are 5 multiple choice. In other words, this is 2 to the 5th. I have 2 choices 5 times, multiplying. All right, then we have 6 multiple choice. 4 for every one of those, right? And so that's going to be 4 to the 6th. In other words, we would do 6 lines and put 4 on each of those and multiply them. Did I lose you at all? Or does that make sense? You sure? You don't look happy with the answer, though. You're just like, man. Yeah.
Why is it times instead of plus for 2 to... Yeah.
Because it's the fundamental counting theorem that it's branches, all right? So let's draw our tree really quick. So we have true or false. Question 1. Either I pick true or false. Well, for the next branch, my next question, I could either have true or false, but I have to go down possible for both of those. So now it looks like plus, right? Because it's 2 plus 2 equals 4. However, if we do the same thing, every one of these has 2 branches.
No, wait. I mean, like, why do you multiply the different types of questions instead of adding them?
Because it's a branch. It's really hard to do the full branching,
Right.
but the long story short is let's say we just had 2 true or falses, and then our next one was our multiple choices of 4. Well, each of these are going to branch into 4 possible things. And every time I didn't plan for having to write 4 on those. But each of those is going to branch into 4, just like instead of branching into 2, you're branching into 4. So the tree doesn't care that it's a multiple choice or what type of question it is. It's just caring that you're multiplying by each one. And that's what multiplication really is each one of these is being added 4, add 4, add 4, so you're really multiplying by 4. Does that make more sense? Other questions?
Yeah, it does.
Okay.
Sorry.
No, you nodded.
Oh, I did.
Yeah. All right, then let's get into today's lesson. Did you have a quick question? You just waited till the last second. Okay. All right, today we're going to talk about combinations, which is a... What is happening, Ross? 43. All right, we'll quickly go over 43. 43 says, choose, you're basically winning a prize. Whoever wins gets one of the 4 VCRs, one of the 3 different CD players, and one of the 6 different CDs available. So you're picking one from each group. So the first group you'll get is one of 4 VCRs. So you'll get one of these if you win. If you win, you also get one of the CD players. And you also get one of the 6 CDs. Well, since I'm getting one of each of these groups, you're just going to multiply them together to give you 72 possible. You get one of each. Yep. All right, today we're going to talk about combinations. And the 2 different things here are the difference between combination and permutation. I just combined the word into convertation. All right, the first one says, my fruit salad is a combination of apples, grapes, and bananas. As long as you have each of those in your salad, you're good, right?
Are the bananas peeled?
I don't know.
No, they just dropped a whole banana.
Yeah. Who cares? It's a whole banana. They put it in there. You're okay as long as it's all in your fruit salad. You don't care if they put the grapes in first and the next one, and then they stirred it up. So order does not matter on this one. You don't care which one in first, which one in second, which one in third. However, if you're doing a combination and you do it out of order, it doesn't work. The order in which you put these in matters. The order at the end affects the outcome. This order does not affect the outcome. You just have a bowl of fruit. This one, you either open something or you don't open something. That's going to lead us to 2 specific words you need to know for this little section. And that is, when the order doesn't matter, you use combination. When order does matter, you use permutation. So the fruit salad example would be an example of a combination. The example of a safe would be an example of a permutation. Which means your combination lock is actually misnamed. It should be a permutation lock. Combination would mean you just need to know your 3 digits and just however you do it, it opens. Maybe it does. Have you tried it? No. Maybe you should try it. Maybe it actually is a combination lock. All right, so the big thing in today's lesson is deciding whether order matters or doesn't matter, and I'll talk about ways that you can delineate it. It is slightly more difficult than it sounds on several cases. So first, let's compare permutation and combination. First of all, for a permutation, order matters. For a combination, order does not matter. Some notation for permutation. We already did one yesterday, and that is where you have your capital P. And you put your... How did I label it yesterday?
Oh, N minus R.
N minus R. Yeah, N comes first. Every book has them slightly different, where the N and R's are different places and stand for something else. The other way you might see it written in like a math book or something is you might see a capital P with the N on the left side and the R on the right side.
That's lame.
It is not lame. Combination actually has 3 different ways to write it. The first way looks exactly like permutation except for with a capital C. We're going to have N and R. The next one looks a lot like the permutation as well, where you have a capital C and the N and the R flanking it. The last one is slightly different. This one is not going to have a capital C in it. It's just going to have a parentheses with an N over R stands for combination. Every one of those stands for combination. All right, let's get to the formulas. The good thing is they're very, very similar. First of all, our permutation one was N factorial over N minus R factorial. Combination is going to look identical minus one little addition. And that is N factorial over N minus R factorial. So it looks exactly the same right now, but we're going to add something onto it. And I'll talk about why you're going to add something onto it. In combination, order does not matter. So what you need to do is get rid of all of the ones where order mattered, where like 1, 2, and 3 would be the same thing as 3, 2, and 1 as long as you pick the same 3. Combination are going to have a lot less. So you're going to multiply the bottom by R factorial. All right, those are our 2 formulas. Those are your major ones. Let's go through our examples. Example 1. A 3-person committee is needed to study ways of improving public transportation. How many committees could be formed from 8 people on the board of supervisors? So your goal is going to be, does order ultimately change what happens? What I mean by that is I pick 3 people. I grab 3 people and I throw them in a committee. Is there anything that delineates between whether you're committee member number 1, 2, or 3? No. So I'm just going to grab 3 people. I'm not going to organize them. I'm just going to take 3 people and throw them in a committee. There's no organizing. There's no order to them after I grab them. So does order matter? No, it doesn't. 3 people, doesn't matter how I'm standing around, I'm just grabbing 3 people and throwing them in a committee. Yes?
But like, how does it not matter? Because you don't want to put the same person in
Well, I'm just saying order doesn't, you're only picking 3 people. We have 8 people, and what they're saying is grab 3 of them and put them in a committee. How many different ways could I have grabbed 3 people? Yes, yep. Since order doesn't matter, we're going to use combination. And since it's combination, we're going to do our cap C. And we're going to say, okay, we started with 8 people. And we're seeing how many different ways I can pick 3 of them. Well, the formula for that is going to be 8 factorial divided by 8 minus 3 factorial times 3 factorial. Now, stay with me here. There is most likely, because every year I have, there is going to be a section on here where you can't use your calculator. You don't need your calculator on this one. Bless you. Because let's work our way down. All right, we have 8 factorial over 5 factorial times 3 factorial. I'm going to rewrite that. 8 factorial is actually 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So it's really 6 times 5 factorial. I can stop there and put a factorial symbol on it. Over 5 factorial. And I'm going to rewrite 3 factorial as 3 times 2 times 1. 5 factorial will cancel out with 5 factorial. It's the same number. 3 times 2 is 6. Well, there's a 6 right there. So we can cancel out our 3 times 2 times 1, really, because that's all 6. And our whole answer is 8 times 7, which is going to equal 56. If you do not know how to do that, you're not going to be able to have time to do the part where you can't use your calculator, because otherwise you're going to be the person that by hand is going to try to do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then you'll have to do 5 times 4 times 3 times 2 times 1 times 3 times 2, and then you're going to have to divide it all out. Versus scratching some stuff out, and your answer is 56. All right, so that's a combination problem. Our next one says you have 12 students helping a project. The director needs 3 telephone solicitors. He also needs 4 door-to-door solicitors, and he also needs 5 magicians. They all seem like very on-par jobs. In how many ways can these jobs be assigned? Let's look at it individually. We're trying to pick telephone solicitors, and then door-to-door solicitors, and then magicians. When I grab 3 people and tell them to call or do whatever they're doing with their telephone, does the order matter once I grab the 3 people? No, you're all doing the same job. All right, when I grab the 4 people to go door to door, is there any organizing those 4 people once I grab them?
No.
Nope, they're all door to door people. And finally, when I grab 5 magicians, there's no organization. Once I grab the 5, there's no hierarchy. There's no like manager level or anything. They're all the same people. They're all magicians. So order does not matter on any one of these. We're looking at it individually. So order does not matter. Nope. So that means we're going to use combination. And we're going to use combination 3 times. Because we're going to treat this as 3 different problems. The first problem is I have 12 students, and I'm going to choose 3 of them to be telephone solicitors. That is going to be a combination where we start with 12, and we're going to choose 3 for our telephone. All right, now we're going to have a new combination. How many people do I have left?
9.
I have 9 people left. So this one's going to be 9, and we're going to choose 4 door solicitors from that 9. So this is going to be 9, choose 4 for our door knocking campaign. Now finally, how many people do I have left?
4.
5. We have 5 people because we are choosing 5 magicians. It'd be weird if you had 4 and we had to choose 5 magicians. Well, it's magic, right? Ooh. All right, it might not look like it. So I have 3 combination problems. This is breaking down to the fundamental counting principle. Rather than choosing 1 from each of these, I'm choosing 3, I'm choosing 4, I'm choosing 5, but it still comes down to the counting principle. If you're choosing something from each group, you're just going to multiply all of those together. It's going to be your first choices times your second choices times your third choices. If you did a tree diagram, you'd see they all map together. All right, and that's going to equal, well, we're going to have 12 choose 3, which is going to be 12 factorial, over 12 minus 3, which would be 9 factorial, times 3 factorial. If you need to, make sure you put 9 actually comes from the fact that you're doing 12 minus 3. I just don't have a lot of room. I got to write pretty big. Our next one is 9 factorial over 9 minus 4, which is 5 factorial, times 4 factorial. Remember, this 5 just comes from the fact you take your n minus your r. So that'd be 9 minus 4 gives you that 5. And finally, we are going to have our 5. Choose 5, so that'd be 5 factorial over 0 factorial times 5 factorial. 0 factorial equals 1. Don't forget that. That isn't 5 divided by 0. That's impossible.
Wait, is 0 from the 5 minus 5?
Yes. Oh, sorry. I didn't write that down, did I? That'd be 5 minus 5. Yep. Real quick, let's think about this. If I have 5 people, and I need to pick 5 people in order doesn't matter, how many ways are there for me to pick those 5 people?
1.
There's one way. What's 5 factorial divided by 5 factorial? 1. So you probably, if you were really quick, you would realize that you don't even need to do that last one. You just know 5, choose 5. 5 people, pick 5 people. The order doesn't matter. There's only one way. I grab all 5 of them and say you're magicians. All right. Now let's break this down a little bit. Make it a little simpler on ourselves. So I'm going to look at that 9 factorial on the bottom, and I'm going to cancel that out with the 9 factorial up here. Then I'm going to say that 5 factorial divided by this one, that's just 1, so I don't need to deal with that one. So this, we could go further, but I'm going to stick with the 12 factorial over, it'd be 5 factorial times 4 factorial times 3 factorial. This might be one that I wouldn't put as no calculator. This one would be one I would let you use a calculator on most likely. We could go further, but let's talk about how to use your calculator to do this. You have a math button on your calculator. Let's find our math button. And then you're going to hit right all the way, and you're going to get to a probability section.
Oh, yeah, I heard this.
That probability section has an exclamation point, which is your factorial. Now you can type in 12 factorial divided by 5 factorial divided by 4 factorial divided by 3 factorial. I'd be very careful to make sure to put your denominator in parentheses. I always put my numerator in parentheses, and I put my denominator in parentheses. I overuse parentheses because the last thing you want to do is get the wrong answer for typing something in your calculator. So I would type in 12 factorial divided by, in parentheses, 5 factorial times 4 factorial times, I'd probably just do 6. Because 3 times 2 times 1 is 6. Yes? All the way to the right. If you go all the way to the right, there should be a probability. Yep. And there you go. This should equal a number. Am I right?
It does.
It does. All right, what do you get?
27,720.
27,720? Ooh. Oh, yours is a little low. Yes, it's 27,720. All right, let's move on to the next one so we don't run out of time. I only got 10 minutes. I got to get through some important stuff. All right, this one says 50 people purchase raffle tickets. 3 winning tickets are selected at random. First prize is $500, second is $100, third is $50. How many different ways can the prizes be awarded? So I grab 3 people and I say you win. Do I now organize those people in a specific way?
Yes.
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 Now I take those 3 people and I say your first, your second, your third. So if the people you take you then organize, then order matters. So order matters on this one. Yes. C. Then you have to use permutation. All right, so if we're using permutation on this one, we use cap P. And then we'll say, okay. How many people did we start with? We started with 50. And we're going to pick 3 people to win. That formula is going to be 50 factorial over 50 minus 3 factorial, which is 50 factorial over 47 factorial, which I could then simplify further to being 50 times 49 times 48 times 47 factorial, all over 47 factorial. Our 47 factorials cancel out. So in our calculator, all we have to do is 50 times 49 times 48. So this could easily be done on a scientific calculator, and we would have 117,600 600 possibilities to get those 3 winners. All right, so that's permutation, that's combination. We had 2 levels of combination. One was hard, one was a little easier. All right, the next thing I want to talk about is identical objects. You have 11 letters that spell out the word Mississippi. How many ways can I rearrange Mississippi, and how many words can I come up with by rearranging them? They're not really words, but how many different ways can I rearrange it to have a different arrangement of letters? Here's where the problem comes in. Lots of words are going to be repeats, i.e., let's say I switch around these 2 S's. I still have Mississippi. That isn't a new combination. If I switch these 2 I's, that is not a new combination. So we have to account for all the ones that you'll change, but isn't a new combination. That is repeat letters. You can read all this, but we're just going to do the example. It makes more sense when we do the example. So our example is Mississippi. So like I said, unless I miscounted, there are 11 letters.
You counted right.
Thank you. So if I was just told how many different ways are there to rearrange this? Well, if you think about it, for the first letter, you have 11 possible letters to pick from. Our next letter, we're now down to 10 possible letters. Then we have 9, 8, 7, 6, 5, 4, 3, 2, 1. So without accounting for repeat letters, we would have 11 factorial possible ways to rearrange those letters. Now we have to tackle all of the ones that are repeats. Like Mississippi isn't a new letter if I just switch around my S's. In order to do that, we're going to count our repeats. So we're going to say M. How many times does M show up? It shows up once. And then we have I. How many times does I show up? 4 times. How many times does S show up? 4 times. And then we finally have P's.
2.
We have 2 of those. 4 plus 4 is 8 plus 2 plus 1 is 11. Awesome. All we have to do to get rid of those extras is we're going to divide by each of those with a factorial after it. So we'll have 1 factorial, which is useless. It's just 1. 4 factorial times 4 factorial times 2 factorial. We really don't have time to let you guys plug that in, but you're going to end up with 34,650. So you come up with your normal number of possibilities, and you divide by each of your repeats in factorials. I say this every single year. This is buried on the bottom of kind of a lesson. It's still important. It'll show up on the test. You have to know identical objects. I'm just not going to spend a whole bunch of time because that's it. All right. We're not done, by the way. I still have 5 minutes to finish the last problem we're doing together.
Of that page.
Of that page. All right, we still have one more problem. This one isn't that hard because I did throw in that it's a lot like the one with telephone, door knockers, and magicians. It's a very similar concept. It is, we have a company of employees that has 9 males. We have 7 females, and they're trying to make a committee that has 3 males on it and 2 females on it. First of all, we have to decide if order matters or doesn't matter. So let's look at the guys. All right, we have 9 employees. I take 3 of them and put them on a committee. Do I organize them after I pick the 3? Are they being organized, or are they just on a committee? No. So order doesn't matter. Order does not matter. Order only matters if after I grab those 3, if I was like, we have a committee that I need a president, a vice president, and a secretary. So if I grab those 3 people and I say, then further subdivide them, then order matters. But all we're doing is putting all 3 on the same committee. So order doesn't matter. So for the guys, we'll put the men. We are going to have a combination where we have 9 employees, and we are going to pick 3 of them, or choose 3 of them, to be on the committee. Then we're going to do the same thing for the women? Well, the women only have 7 people employed by this company, so they're only going to choose 2 of them to be on the committee. Now we're going to use the fundamental counting principle to say, well, if you're having a group and you're picking some, and you have another group and you're picking them, you just multiply them together and you come up with your total possibility. So we're going to multiply those 2 things together. Well, that's going to equal 9 factorial divided by 9 minus 3, which is 6 factorial, times 3 factorial. Remember that 6 just comes from the 9 minus 3. Feel free to write that down. I just don't have space or time. Then we're going to multiply that by 7 factorial over 7 minus 2, which is 5 factorial, times 2 factorial. Remember that 5 comes from the 7 minus 2. All right, there are ways to rewrite all of this to simplify it. I'm just going to give you the answer. It is a little. Basically, 9 factorial over 6 factorial times 3 factorial is 84. That'd be times 21, and you'd come up with 1764. But you should, on this homework, practice 2 different ways. Using your calculator, make sure you know how to use your calculator, and make sure you know how to do these by hands, especially the simple ones. Like number 3. Number 3 you should not need a calculator for. In fact, several of these you should not need a calculator for. All right, guys, have a wonderful weekend.